course, today we are going to start talking about real-world processing in memory architectures, and in particular, we will talk about the one that was the first released and commercialized, the UPMEM PIM architecture. As you already know, because we started introducing this in the previous lecture, PIM is becoming a reality. In 2019, UPMEM started to commercialize their PIM-enabled DIMMs. We are going to talk in detail about them today. But more recently, in early 2021, Samsung announced the FinDRAM architecture, and later one more, the AXDIMM proposal later in 2021, and quite recently in February this year, SK Hynix, another major DRAM vendor, announced their accelerator in memory that we will also probably talk about in later lectures. This is the announcement of the Samsung FinDRAM architecture. Remember, this is an architecture targeted at machine learning, inference of machine learning and AI, and this is the SK Hynix accelerator in memory. It's a GDDR6 based PIM architecture, also with machine learning in mind and high performance computing, big data computation and storage. Remember also this slide about the UPMEM architecture. Remember the UPMEM DIMMs, the PIM enabled DIMMs containing PIM chips. Inside each PIM chip we have memory arrays and small processors called DRAM processing units, or DPUs. We are going to talk in detail about these DRAM processing units today. And following a relatively simple approach, in the sense that it's also nearbank, we find this Samsung FinDRAM in the HBM2 memory, where some of the HBM layers have been modified to embed PCU blocks, or processing elements that are able to perform operations like multiply, add, and multiply accumulate. And the other proposal from Samsung is this AXDIMM is a DIMM-based solution, and the specific prototype that they tested, there is an FPGA on top of the DRAM DIMM and has direct access to the memory in the ranks. We will talk also about AXDIMM in a later lecture. But for today, we are going to focus on the UPMEM PIM architecture, and in particular, the microarchitecture and ISA of the DPUs. Remember that UPMEM fabricates PIM-enabled DIMMs. These DIMMs have these PIM chips containing DPUs that run at a certain frequency. In the very first generation that we were aware of, the UPMEM DIMMs contain 8 chips or 1 rank, and the DPUs run at 267 megahertz. A later generation already includes 2 ranks, 16 chips per DIMM, and the DPUs are able to run at 350 or 425 megahertz. And this architecture, this PIM architecture, is really promising. And why is that? Because it's going to be able to provide massive speed ups and massive energy savings compared to conventional systems. Actually, I like this slide that comes from Fabrice Devol's presentation at Hot Chips 31. And here you can relate what's the normal DRAM, the energy for a normal DRAM access, and compare it to the execution, the energy that is needed for a, for example, double precision operation. Observe the difference between these two numbers, and remember the slide that we saw in the previous lecture, that motivational slide from Bill Daly, where we compared the access in terms of energy to data in memory with the energy consumption of the execution of computation in the cores. And we saw that there were essentially like 2-3 orders of magnitude difference. And this is what we observe here as well. This difference is greatly reduced if we access from a processor residing in memory, as these DPUs that the UPMEM PIM chips have, and you can compare essentially by reducing the access to DRAM by 20 times with respect to a conventional processor, even though the cost of a single operation itself might be a little bit higher. But these are like very promising numbers that for sure will be able to guarantee in very interesting energy savings, at least in some important applications. But achieving all of that is not easy at all. it's really challenging to embed logic, to embed processors into a DRAM chip using DRAM process. And the reason is that transistors are like 3 times slower, the logic cannot be so dense, and also the routing density decreases dramatically. We can say that typical DRAM chips have 3 layers of metal, while in CMOS devices, we typically have more than 10. So this makes very challenging to build fast processors, fast transistors, and fast processors inside the DRAM chip. But still, it's possible to somehow compensate for that by the design of the architecture itself. Like, for example, using a relatively deep pipeline, as we will see, as the DPUs have. UPMEM filed a patent in 2019, and if we take a look at the abstract of this patent, we already see a very clear description of what the system is. The UPMEM circuits, the UPMEM DIMMs contain memory circuit. Inside each memory circuit, there is one or more memory arrays and one first processor. These first processors are the DRAM processing units, or DPUs, and there is a control interface for a central processor that is a CPU to communicate with the first processors or DPUs. And the memory banks become accessible to either the central processor or the first processor, depending on the stage of the execution of the program. This system follows what we call the accelerator model, where we have UPMEM DIMMs, UPMEM PIM-enabled DIMMs coexisting with conventional DRAM DIMMs. And in this accelerator model, the UPMEM DIMMs can be seen as a coprocessor, as a loosely coupled accelerator. Specifically, what we have to do is moving data from the memory of the main processor of the host CPU to the memory of the accelerator or the UPMEM system, the PIM-enabled memory. And once the input data has been moved to the PIM-enabled memory, we can start the execution by explicitly launching a kernel onto the UPMEM DPUs. This model resembles GPU computing, and GPU computing, as probably most of you are familiar with, the computation is offloaded to the GPU, and there are essentially 3 steps. In the first step, we have a CPU to GPU data transfer, where we move the input data from the CPU memory to the GPU memory. After that, we launch one kernel for execution on the GPU hardware, execution by the GPU cores that computes on this input data and produces some output results that are later moved back from the GPU memory to the CPU memory using a GPU to CPU data transfer. So this is how GPU computing works. This is essentially what we call the accelerator model. If you want to learn more about GPU computing, how to program GPUs, I can recommend you several for lectures on GPUs. For example, this one that you have in the slide. And if you want to go into many more details, you can take a look at our heterogeneous systems course that we started teaching and with several lectures in fall 2021, and just this week we also started the spring 2022 edition. So remember, in the accelerator model, the first thing that needs to happen is the central processor or the host CPU, here in this slide called SoC, system on a chip, load data from and move data from the main memory to the PIM-enabled memory. After that, the CPU, the central CPU, can transmit a data processing command to the DRAM processors. That is, we can launch the kernel that will run on the DPUs, on the processors in the memory side. And after that, processing will start on the memory side by these DRAM processors. In the meantime, the CPU checks from time to time whether the execution on the DPU side, on the memory side, got completed. After it's completed, the memory banks become accessible by the central processor, by the CPU, for the CPU to retrieve results from the PIM-enabled memory and move them to the main memory. So this is essentially how the accelerator model works and how the UPMEM-based PIM systems work. We can take a look at this system, at the system organization, and identify here the central processor with its own main memory, typically conventional DDR4 memory, for example. Here we find the DRAM DIMMs, the UPMEM DIMMs with their PIM chips. Inside the PIM chips, we have memory arrays and small processors called DPUs. And here you have another view of the same system where you can identify several DIMMs of main memory connected via memory channels and memory controllers to the host CPU, and also in other channels we find the UPMEM DIMMs or PIM enabled memory, a few of these DIMMs. Inside or on each DIMM, we typically have 8 or 16 chips, as we mentioned before. This is 1 or 2 ranks of 8 chips each, and inside each PIM chip, there are several of these slices. In particular, in the current architecture, there are 8 of these slices. In each slice, we have a 64 megabyte DRAM bank that is called main RAM or MRAM, and we have the DRAM processing units or DPUs. Observe that there is a DRAM processing unit per MRAM bank. So in total, we have 8 DPUs per chip and 64 DPUs per rank. We will take a closer look at this DPU pipeline later, but yeah, here you can already identify the DPU pipeline with several stages and a register file. From this pipeline, we have access to an instruction memory, an IRAM of size 24 kilobytes that can hold up to 4,096 instructions. We also have a scratchpad memory, which is a software managed cache called working RAM or WRAM of size 64 kilobytes. And here this DMA engine to communicate either instruction from the DRAM bank to the IRAM or operands, input and output operands, back and forth between the MRAM and the WRAM. As I said, we are going to talk in more detail about all these different components in today's lecture and in later lectures as well. One of the systems that, or let's say that the current system that UPMEM commercializes is able to have up to 2,560 DPUs. We we're lucky to be able to work with this system, and we are going to show you in later lectures some of the results that we obtained and the characterization that we made of this system. This system actually contains 20 UPMEM DIMMs of 16 chips each, so in total there are 40 ranks. This is a system with a dual socket processor, 2 CPUs essentially, and each of them have their own main memory DIMMs and also PIM enabled DIMMs. In total, as I said before, a maximum of 2,560 DPUs and 160 gigabytes of PIM enabled memory. And here you have a picture of the system itself where you can identify the 2 CPUs, CPU 0 and CPU 1. These are the DRAM DIMMs connected to either CPU 0 or CPU 1 and the PIM enabled DIMMs. We were also working with a smaller UPMEM-based PIM system of 640 DPUs and up to 40 gigabytes of PIM-enabled memory. In this case, it's a single socket CPU. As you see, there are a lot of DPUs in the system, and one good thing of, in general, processing in memory systems, and in particular this UPMEM-based PIM system, is that the compute throughput, the compute power of the PIM system increases with the scaling of memory. So as memory becomes larger, we will have more memory banks. And as we have more memory banks, we will have also more DPUs. So there are so many DPUs in the system that in principle, there is no need for sharing these DPUs across multiple CPU processes. If we have 2 processes, for example, running on a system, and they both want to make use of the PIM-enabled memory, but want to make use of the DPUs, they can allocate and schedule their computation on different DPUs. And this way, we solve some of the potential issues, or we avoid some of the potential issues that may come from sharing the same processor by multiple processes. So this simplifies the security implications, for example, and according to UPMEM, there are no side channels and there's no need for an operating system. So we are going to continue talking about the UPMEM PIM architecture, and we are going to start talking about more and more details about the microarchitecture, about the ISA. But my opinion is that a good way of approaching these learning and these descriptions of the architecture and the microarchitecture, it's by understanding how the software works on this system and how we are going to distribute the workloads on the available resources. So that's why I want to introduce now our first programming example. Very simple thing is a vector addition. I'm pretty sure you all know how we have to perform an element-wise addition of two vectors, A and B, and store the results in an array, output array C. It's an element-wise addition, so we read from memory element A0, element B0, we add them and store the result in position C0 in the output array. How do we perform this computation on UPMEM-based PIM system? In this case, and this is the reason why this is our first programming example, the distribution of the workload is very simple. We just need to partition the input arrays into equally sized chunks, and we assign each of these chunks to different DPUs. So in this case, we have 4 DPUs in the system. So each of them receive one chunk from A, one chunk from B, so that they can compute on them. But inside the DPUs, we have threads running and executing in a multi-threaded fashion. These software threads are called tasklets in the UPMEM programming model. And inside each DPU, we are going to distribute the computation across these tasklets so that they operate on the input data to produce the output results. So for example, here, and assuming that we have 2 tasklets running on DPU 0, this part of the array is assigned to tasklet 0, this part to tasklet 1, and in the rest of DPUs, we distribute the computation across tasklets in a very similar way. But before we start computing on these arrays, we need to move these arrays from the main memory of the CPU to the PIM-enabled memory. And to do so, what we do is using CPU to DPU data transfers, where we move data from the DRAM chips to the PIM chips that you can see in the image. After performing the computation on the PIM-enabled memory, the host CPU can retrieve the results by using DPU to CPU transfers. As we will see in later lectures, there are different types of these CPU, DPU, and DPU, CPU transfers. There are serial transfers when we target a single MRAM bank. There are parallel transfers when we access, read, or write multiple banks at the same time, MRAM banks at the same time. And there are also broadcast CPU to DPU transfers when we target multiple banks, but we transfer a single buffer from the main memory to the multiple MRAM banks. And understanding how these CPU, DPU, and DPU, CPU data transfers work is important not only because the execution of any program on the UPMEM-based PIM system starts and ends with these transfers, but also because during the execution of the program, we need to use them as well for communication across DPUs. All this communication happens via the host CPU because there is no direct communication channel between DPUs. So that's why all inter-DPU communication in the current UPMEM-based PIM system takes place via the host CPU. We will see how this communication may happen, different communication patterns in later lectures, and we will see what are the performance implications of these inter-DPU communication. But now let's go into more details about the processor itself on the memory side, the DRAM processing unit or DPU. Remember in our PIM base or in our PIM system, we have multiple PIM chips. Inside each PIM chip, we have multiple memory banks, and connected to each memory bank, we have a small processor called DRAM processing unit or DPU. This small processor contains an instruction memory where instructions are stored and fetched then issued onto a pipeline that executes the instructions and eventually accesses a local memory, an SRAM-based memory, where it stores operands temporarily. Here in this picture, we can see more clear all the different components of the PIM chip and the DPU. Here we can identify a control and status interface for the CPU to communicate commands to the DPU pipeline. We also have a DDR4 interface because this is DDR memory and it's accessible by the host CPU. So this interface is for the host CPU to be able to access the DRAM banks called MRAM banks, as you know, and these from the DPU are accessed using the DMA engine in order to read instructions and put them here in this IRAM. It's an instruction memory, or operands in this WRAM or scratchpad. Both are SRAM-based type of memories. And finally, here you can see the pipeline, a pipeline of 14 stages that has access to its own register file. And what can we say about this pipeline? Well, what we know about this pipeline is that it runs at a frequency of up to 425 megahertz in the most recent versions of the UPMEM PIMs. It's a fine-grained multi-thread pipeline. These are fine-grained multi-thread processors that can run multiple hardware threads, in total 24 hardware threads. The pipeline has 14 pipeline stages. As you can see in the slide, we have a dispatch stage for thread selection. Every single cycle, we start the execution of one instruction for a different thread, for a different software thread or tasklet, and we decide what's the next thread to be scheduled in this dispatch stage. Then we have a fetch stage, which is or 3 fetch stages for fetching an instruction from the IRAM. Then we read operands from the register file, format these operands, and then start the execution of the instructions in the ALU stages. From these ALU stages, we are able as well to access not only execute here arithmetic operations, for example, but also read and write from this scratchpad or software managed cache that is this WRAM or working RAM. And finally, we have 2 result formatting stages. So in total, 14 pipeline stages. And it's a fine-grained multi-thread pipeline. As I said, if you need to quick refresher on fine-grained multi-threaded, let me remind you that here the hardware has multiple thread contexts. Those are the 24 hardware threads that I just mentioned on the DPUs. A thread context here means a program counter and registers, and in each cycle, the fetch engine fetches one instruction from a different thread. The good thing of doing this is that there is no need for logic to handle control and data dependencies within a thread. Why is that? Because there is no single cycle where there are 2 instructions from the same thread in the pipeline. What means is that there is no way of having control of data dependencies between instructions from the different threads. So this simplifies the execution a lot. The key idea is to switch to another thread every cycle such that no 2 instructions from a thread are in the pipeline concurrently. And this is a way of tolerating control and data dependence latencies by overlapping the latency with useful work from other threads. So the fine-grained multi-threading technique is very interesting because it allows us to hide latencies between instructions from a different thread by executing instructions from other threads. This is like a key technique inside the UPMEM DPUs, but is also a key technique in GPUs, for example, to hide long latency accesses to the memory, for example. If you need like a longer brush up on fine-grained multi-threading, I can recommend you this lecture from Professor Mutlu, and here you have a couple more links to other relevant lectures. So remember, the DPU pipeline is a fine-grained multi-thread pipeline with up to 24 hardware threads and 14 pipeline stages. in this pipeline, we execute instructions from the ISA, from the instruction set architecture. The DPU ISA is a specific 32-bit ISA, is RISC style, but is not RISC-V. It's aimed at scalar in order and multi-thread implementation and allows compilation of 64-bit C code as well. The compiler is based on LLVM and Clang. You can, from here, from this link, access the documentation about the ISA and learn much more about the format of the instructions and about the different type of instructions that the hardware natively supports. We will talk about this in later lectures as well. But just as an introduction to this ISA, let me show you some micro benchmark for integer, 32-bit integer addition on the elements of an input array. Here you can compare the C-based code that we as a programmers write in high-level programming language, and here you see the compile code in the UPMEM DPU ISA. As you see, it's a for loop that goes over an array of a certain size. In this case, size is 256 elements. We read one element from the array into a temporal variable, we add one scalar, and then we store in the same position. And how does this compile to UPMEM DPU code? This for loop compiles to this move instruction where we initialize the index I that now is in R2. At the end of each iteration, we update the value of the index and we jump if the index is not yet equal to the bound to 256. Here you can see the access to the memory. In this case, is an access to WRAM, to the scratchpad, the SRAM-based scratchpad inside the DPUs. But first of all, we need to calculate the address with this instruction here. Here we have the addition itself, simply an add operation. And finally, we store the result to WRAM. And here you see another view of actually the same code. In this case, it's obtained by using a very useful tool, the Compiler Explorer. And in particular, in this slide, we are comparing the code for 32-bit benchmark and 64-bit benchmark of this addition micro benchmark. The key difference between the compile codes, as you see, they are almost the same. The key difference is this add C instruction that is used to add the upper 32 bits of the 64-bit elements that we are operating on in the 64-bit micro benchmark. So as you see, even though it's a 32-bit ISA, it's possible to compile 64-bit C code into this 32-bit ISA. And in this case, the codes for 32-bit and 64-bit operands is essentially the same. It's only one instruction from 6 instructions to 7 instructions for the 64-bit addition or subtraction, because subtraction is essentially the same as this one for this macro benchmark. I will show you in later lectures more about this micro benchmark and other micro benchmarks that we developed to understand the internals of the UPMEM PIM architecture. And this understanding covers the different parts of the DPU, from the WRAM bandwidth, how the DPU pipeline accesses this WRAM, this scratchpad or memory for temporary operands. We will also study how the data is moved back and forth between MRAM and WRAM, and we will obtain latency numbers and bandwidth numbers for the communication between these two memory spaces. We will also connect the access to MRAM to the execution on the DPU pipeline and the arithmetic throughput that we can obtain in this pipeline, and also the operational intensity that the workloads themselves have. And we will see how the latencies in the pipeline relate to the latencies in the access to the MRAM. And this way we will understand much more about this architecture. As I said, we will talk about that in our next lecture. So in upcoming lectures, we will cover this micro benchmarking of the UPMEM DPU. We will study the compute throughput, the bandwidth to the two main memory spaces, the MRAM and the WRAM, we will study the relation between the arithmetic or operational intensity of the workloads and the compute throughput that we can obtain in this system. And in later lectures, we will continue talking about the UPMEM-based architecture, learning about how to program it, and explaining our experiences with the benchmarking of this architecture and with different compute patterns. It's not the only architecture that we are also going to talk about in this course. We are also going to devote the specific lectures to the Samsung and SK Hynix PIM architectures, as well as other research proposals covering processing using memory architectures, prototypes, and also other aspects of processing in memory or other aspects of the system that need to be taken into account to enable seamless integration of processing in memory capabilities in real systems. But if you want to learn more about the UPMEM PIM architecture, I can recommend you our paper that is available in archive, or this talk or other talks that we have given about this architecture. If you are impatient, but if you can wait for the next lecture of our PIM course, we will continue talking about it, talking about the UPMEM PIM architecture and other real-world processing in memory architectures. Let me know, send me an email, ping me anywhere if you have any questions about this lecture, about other lectures, about the contents of the course. I'd be glad to get in touch with you and solve any questions you may have. Thank you very much for your attention. See you in our next meeting.